Today we're going to talk about power in three-phase systems. I'm going to start by talking about instantaneous power, and realistically, you guys can just kind of pay attention. I'm not going to actually test you on any of this. I just want you to understand what's going on. So I believe we talked very briefly about instantaneous power in single-phase systems. And I came up with a really large and gross equation, and we're going to effectively wind up with three of those. Let's see, instantaneous power in three-phase systems. So I don't know why everybody decides they need to text me at 8 o'clock in the morning today, but I've got like 8 texts in the last 3 minutes. So let's say that we have just a simple three-phase, three-wire system, like we talked about when we were introducing three-phase systems. And specifically, I'm going to be dealing with a balanced system here, right? So, this is going to be VAN of T like so. Here's my transmission line impedance. Even though I'm dealing with things in the time domain, for lack of a better way to express things, I'm going to put that as an impedance. And then over here, I'm going to have my Y-connected load impedance. And let me just duplicate this a couple of times. Something akin to this. All right. Here's VBN as a function of time. Actually, goodness gracious, my handwriting's looking god-awful this morning. And here will be VCN as a function of time. And then over here on the load side of things, we should see a voltage drop of VAN as a function of time, where I'm using the capital letters to indicate that we're on the load side of things. Sorry, that should be B. And this should be C. And I should also have some phase currents. Like so. So when we were talking about instantaneous power, with regards to a single phase system, so I'm just going to put this as P one phase as a function of time. We simply had our voltage as a function of time multiplied by our current as a function of time. And then we wound up getting a relationship that looked something like 1/2 VM IM cosine theta V minus theta I plus 1/2 VM IM cosine twice omega t plus theta V plus theta I. Okay. Well, in a three-phase system, we are going to have essentially three instances of this equation, and the total power in our three-phase system is just going to be those guys added together. So I want us to see what happens when we look at that, okay? So for our three-phase system, I'm going to explicitly say that the phase angle of, let's do it like this. The phase angle of VAN is going to be 0 degrees plus some theta v. The phase angle for VBN is going to be negative 120 degrees plus some phase angle theta v. And the phase angle for VCN of t is going to be negative 240 degrees plus some phase angle theta v, so that my voltages are 120 degrees out of phase with each other. And I'm going to do something similar for my currents, except that instead of having theta v, I'm just going to have theta I. So it doesn't really matter what the phase angle is, as long as they're separated by 120 degrees in total. Okay. So on my A phase, this is going to look like 1/2 Vm Im cosine. So I'm going to have theta v plus 0 degrees minus theta I plus 0 degrees. So that's still going to look like theta v minus theta I. And then I'll have plus 1/2 Vm Im cosine twice omega t. And now I'm going to add theta v and theta I together. So for the A phase, that's going to look like theta v plus 0 plus theta I plus 0 is still just going to look like plus theta v plus theta I. And I'm just going to put a little note underneath here. This is our A phase contribution. Now down here below, I'm going to have plus, and so we're going to do the B phase, and this is going to look incredibly similar. So we're going to have 1/2 Vm Im cosine. So now I'm dealing with theta v minus 120 degrees minus theta I minus 120 degrees. So effectively what I'm going to see is that that minus 120 degrees minus negative 120 degrees cancel each other out. And I'm going to be left with, once again, a factor of theta v minus theta I. And then I'm moving on to the AC term, and I'm going to have a Vm Im cosine twice omega t. And now when I add those guys together, that's going to look like plus theta v plus theta I minus 240 degrees. So this whole thing is what's going on in my B phase. And then lastly, I'm going to have to take into account what's going on in my C phase. So I'll do that down here. So I'd have 1/2 Vm Im cosine theta v minus theta I, where theta v is this guy right here. Theta I is the same thing, except that I'm replacing the theta v with the theta I. And so I'm going to have minus 240 minus negative 240. And once again, those guys are going to cancel each other out. So theta v minus theta I plus 1/2 Vm cosine twice omega t. When I add those angles together, I'm going to wind up getting plus theta v plus theta I minus 480 degrees. And that's what's going on in my C phase. So this is the total complex, or excuse me, the total instantaneous power absorbed in a balanced three-phase load. Now, we can make this look a little bit prettier, okay? So for example, that first term in the A phase, the first term in the B phase, and the first term in the C phase are all literally the exact same thing. So I can just add those guys together. And so that means my instantaneous power is going to look like, 3/2 Vm Im cosine theta v minus theta I. And now I have those AC terms. But notice that the AC terms are essentially the same thing, except they are shifted from each other by 240 degrees, right? So the A phase, we have a phase angle of 0. In the B phase, we have a phase angle of negative 240. And the C phase, we have a phase angle of negative 480. So what's going to happen when I add those three second terms together? So what happens, throw it in a calculator if you want to. If you did one angle 0 plus one angle negative 240 plus one angle negative 480. So that's one angle 0. Sorry, what? 0 angle 0, which is just a fancy word for 0. So essentially, all three of those AC terms wind up canceling each other out when you add them together. So that means that the instantaneous power absorbed by a three-phase system is just this guy right here. What's interesting about this, and let me preface this, this is only true for a balanced system. So Vm is just the magnitude of the sinusoidal voltage across one of the phase. That is a constant. Im, just like before, is the magnitude of the sinusoidal current flowing through one of the phases. That is a constant. Theta v and theta I, the phase angles for those sinusoidal signals, are also constants. And so the cosine of theta v minus theta I is a constant. So in a single phase system, we had a sinusoidally oscillating power that had a DC offset. In a three-phase system, we just have the DC offset. So the instantaneous power that is absorbed in this system is a constant value. This is one of the greatest advantages of using three-phase power for things like rotating electrical machinery, because if we're able to supply a constant amount of power to the motor as a whole, that means that it's able to supply a constant amount of torque. There's not vibrations or pulses or anything like that. It just absorbs a constant amount of power, generates a constant amount of torque to turn our shaft or something like that. So this is one of the biggest reasons why we use three-phase induction machines in industrial applications. They essentially last forever because they have so little wear and tear on them, because it's a three-phase system where the torque generated is fully constant. Okay. So you may, you guys may not remember this, but if you look back in your notes from, I believe, probably the first or second day of class, when we were looking at that instantaneous power relationship, we said that that first term was the average power, and then the second term was the AC part. Well, we only have an average power term here, or a DC term here. So this is actually our expression for the average power absorbed by a three-phase balance system as well. So the instantaneous power and the average power are literally the same because we're only absorbing a constant amount of power. Okay. So I'm going to put a box around this, and then we're going to look at these relationships from a slightly different perspective. Now we're going to look at things in terms of a complex power perspective. So we're not really worried about sinusoidal oscillations and all of that kind of stuff. We're going to look at things using our RMS phasor domain descriptions. Okay. So I'm going to draw another three-phase YY system. So there's my RMS phasor voltage VAN. my RMS phasor voltage VBN, my RMS phasor voltage VCN, my transmission line network, which will be balanced, so it'll just have an impedance of ZW on each phase. And lastly, my Y-connected impedance. Like so. I'm going to call the voltage drop across this phase of my impedance VAN capitals. This will in turn be VBN, and this will in turn be VCN. And similarly to what I did in the instantaneous power, I'm also going to be looking at my currents. I'm going to be a little bit more explicit with what's going on here because I expect you guys to actually be able to do this. So let's say that our voltage VAN is VP with an angle of, actually, let me do this, is theta V plus 0 degrees. And similarly, VBN is VP with an angle of theta V minus 120 degrees. And VCN is VP with an angle of theta V minus 240 degrees. Similarly, we could say that IAN is going to be IP with an angle of theta I plus 0 degrees. IBN is going to be IP with an angle of theta I minus 120 degrees. And lastly, ICN is going to be IP with an angle of theta I minus 240 degrees. So those VPs are the magnitude of our phase voltage across our impedance. They are going to be the same in a balanced system. So all three of those VPs represent literally the exact same number. And similarly, IP is just the magnitude of the phase current flowing through each of the phases of our Y-connected load here. Okay. So if I wanted to calculate the complex power absorbed by the A phase of this system, I could just use our fundamental definition for complex power, which would be voltage times the complex conjugate of the current. So that would be simply VAN times IAN conjugate. Well, if I substitute in my numbers or values for this, that's going to look like VP with an angle of theta V plus 0 degrees multiplied by IP with an angle of, so I need to flip the sign. So that's going to look like negative theta I, and I'm just going to put minus 0 degrees for what it's worth. Okay. multiplying these two polar form complex numbers together, I'm just simply going to get VP times IP is my magnitude with an angle of theta V plus negative theta I. So that'll be just theta V minus theta I. For the B phase, I'm going to have VBN times IBN conjugate. And so that's going to look like VP with an angle of theta V minus 120 degrees times IP with an angle. So now I'm taking the conjugate of theta I minus 120 degrees. So that's going to look like negative theta I plus 120 degrees. I just have to flip the signs fully on that angle. And once again, to perform multiplication with phasor numbers, I simply multiply the magnitudes together. So I'm going to get VP times IP, and then I add the angles together. So I'm going to have theta V plus negative theta I. So that's going to look like theta V minus theta I. Then I'm going to have negative 120 plus 120, which cancels out to be 0. So our B phase complex power is literally the exact same thing as our A phase complex power. We'll see here, and I'm going to do this one pretty quickly, that we're going to have the exact same result with our C phase complex power. So that we would have VCN multiplied by ICN conjugate. So that'll be VP angle theta I minus 240 degrees, IP angle negative theta I plus 240 degrees. And this will once again come out to VP IP angle theta V minus theta I, or the same thing as SB, which is the same thing as SA. So our total three-phase power, so S total is just SA plus SB plus SC, which is the same thing as 3 times SA, or 3 VP IP angle theta V minus theta I. So this is our first relationship. I'm going to rewrite it down here underneath because we're going to manipulate it in a moment. So the total complex power absorbed by our three-phase load is 3 VP IP with an angle of theta V minus theta I. Now, we express everything in this relationship in terms of our phase voltages and our phase currents. So this is a phase quantity representation, but we can do a little bit of math, not a whole hell of a lot. And what we can actually find out is how to express our total complex power in terms of line-related quantities. So line currents and line voltages, okay? So let's go back up to our diagram here, okay? So our line current, IAA, is related to our phase current, IAN, in what way? How are the currents IAA, which I have indicated up there in red, and IAN, which I have indicated to the right of that in blue, how are those two currents related to each other? Say it louder. They're the same thing. They are the exact same thing, okay? So I could, if I were so inclined, leave this right now, and this is going to be an intermediate step, as 3 times VP times IL, where IL is the magnitude of my line current, with an angle of theta V minus theta I. Okay. Now, how are the voltages VAN and VAB related to each other? What was that? They are not the same.
Oh, they're the different by degree, by degree.
Nope. Square root 3 angle 30, right? So VAN multiplied by root 3 angle 30 gives us VAB. So the magnitude of VAN, which is VP, if I multiply that magnitude by the square root of 3, I will get the magnitude of VAB, right? So what I'm going to do is I'm going to replace that 3 times VP with square root of 3 times the square root of 3 VP IL angle theta V minus theta I. So square root of 3 times square root of 3 is just 3, right? But I know that the square root of 3 multiplied by VP is just the magnitude of my line voltage. So that's going to give me square root of 3 VL IL with an angle of theta V minus theta I. Ricky, you're making a face.
Yeah, where we leave this.
Yeah, so I'm just splitting that 3 up into square root of 3 times square root of 3. So if I split 3 up into root 3 times VP, and then in the next step, if I realize that root 3 VP is just VL, that allows me to express my total complex power only in terms of line current magnitudes and line voltage magnitudes. And then the angle of the difference in between those quantities, right? Where, just to be clear, this theta V minus theta I, let me take this out a step further. So this is going to be 3 VP IL with an angle of theta Y, where theta Y is just the angle of the impedance, the Y connected impedance, right? And so I want to be clear that that's the same exact angle that we're using down here. So 3 VP IL angle theta Y. So this is a relationship for total complex power. Oh goodness, that is wrong right there. Sorry. That should have been, goodness, this needs to be black. Root 3 VL IL angle theta Y. Sorry about that. Okay. So let's see what would happen if we had a delta connected load. Okay. since we derive those relationships for a Y-connected load, let's see what shakes out when we have a delta-connected load, right? So on the source side of things, it really doesn't matter. So I'm just going to do that as a Y-connected source yet again. So here's VBN, here's VCN. Here's my impedance ZW. ZW. And ZW. And then I need to have a delta connected load here. So I've got one phase connected between the A and B, one phase connected between B and C, and lastly over here, one phase connected between C and A. And I'm going to define the phase voltage here as VAB, the phase voltage here as VBC, and the phase voltage here as VCA. Here's my phase current, IAB, my phase current, IBC, and my phase current, ICA. And let's say that VAB is VP with an angle of theta V plus 0 degrees. VBC is VP with an angle of theta V minus 120 degrees. And VCA is just magnitude of our phase voltage, angle theta V minus 240 degrees. Expressing my phase currents, that might look something like IAB is IP angle theta I plus 0. IBC is IP angle theta I minus 120, excuse me. And lastly, ICA is IP angle theta I minus 240 degrees, right? So we know that in a balanced three-phase system, even in a delta connection, we know that our phase voltages will have the exact same magnitude as each other, but they will be shifted in phase by exactly 120 degrees. And we know that our phase currents, even in a delta connected system, will have the exact same magnitude. They will be shifted in phase from each other by 120 degrees. So if I were to formally calculate complex power absorbed by the A phase, would it be literally any different than what I did up here? No, nor for the B phase, nor for the C phase. So for this delta connected load, we should essentially see that our total complex power is going to be 3 VP IP with an angle of theta delta, where that is just the angle of the delta connected impedance. So it's essentially the exact same thing. It's just 3 multiplied by the magnitude of the phase voltage multiplied by the magnitude of the phase current with an angle of whatever the phase angle of the connected impedance is. Okay. Now, what is the relationship between our phase voltage VAB and this line voltage VAB? They are literally the exact same thing. We mentioned this a couple of class meetings ago. In a delta connected anything, the phase voltages and the line voltages are identical to each other. So I could replace that VP with a VL. So that would look like 3 times VL IP angle theta delta. Okay. Now, what's the relationship between my line currents and my phase currents in this delta connected system? So IAB multiplied by √3 angle negative 30 degrees is IAA. So I take my phase current, IAB, multiply it by √3 angle negative 30, and I get my line current. So the difference in magnitude is once again just a factor of the square root of 3. So if I split that 3 up into √3 by √3 again, here I have VL, here I have IP angle theta delta, and I realize that √3 times IP is just IL for a delta connected load. I wind up getting √3 VL IL angle theta delta. So essentially, what I'm trying to get at here is that it literally doesn't matter if we have a Y-connected load or a delta-connected load, as long as we can figure out either the phase voltages across the load or the line voltages across the load, the phase currents through the load or the line currents through the load, and the angle of the impedance, we can calculate the complex power, regardless of how things are actually configured, okay? So, summarizing here, then, we can say that the total complex power absorbed in a three-phase system is either going to be expressed as 3 times VP IP with an angle of, now I'm just going to call this theta Z, where this is just the angle of the impedance. I do not care whether it is a Y-connected impedance or a delta-connected impedance. It literally doesn't matter at all. Or it could be written as √3 VL IL angle theta Z. So I have one expression dealing with phase quantities and one expression dealing with line quantities. So depending on what I'm given or what's easiest to determine will tell me which of these two equations to use. Let's take this a step further, okay? So our average power, and I'm going to do this, actually, I'm just going to call this P three-phase. So this is our three-phase average power. That's just the real part of our total complex power, right? So that would be 3 VP IP cosine theta Z, or √3 VL IL cosine theta z. And I'm just going to put a note out to here. This is just the real part of what I called S total a moment ago. Our reactive power is going to be 3 VP IP sine theta z, or root 3 VL IL sine theta z, which is nothing more than the imaginary part of my total three-phase complex power. My apparent power is just going to be 3 VP IP, or root 3 VL IL, and my power factor is going to be, once again, just the ratio of P three-phase over my three-phase apparent power. And so that's literally just cosine theta z, regardless of whether we have line quantities or phase quantities. So power factor for a single phase system is literally identical to the power factor in a three-phase system, assuming that we have a balanced load. All right, so let's take a crack at this ICA now. I know that I've hit you guys with a lot of relationships, but really, you can think about this in two ways. You can either just treat everything as if it was single phase loads and add them together, so it's nothing that we didn't do earlier. Or in a more generic sense, you just need to know phase quantities or line quantities, and you're good to go. So in this first problem, we have two different three-phase loads. We have a first load absorbs a total of 60 kilovolt amperes at a power factor of 0.8 lagging, and the second load draws 30 kilovolt amperes at a power factor of 0.75 lagging. So I'm going to try to draw a little picture that represents this. I want you guys to notice that I wasn't told whether my source was connected in Y or delta. And I also wasn't told whether my loads were connected in Y or delta. I know regardless of whether I have a Y connection or a delta connection, I'm going to have access to those three transmission line terminals on both my source and my load. So because that's how I connect them together. So those are the only terminals that I have that I'm sure of. So I might represent this system as something like this. So this is literally just a black box representing a balanced three-phase source. Here's terminal A, B, and C. Then over here, I'm going to choose to put load 1. We are told that it draws 60 kVA at a power factor of 0.8 lagging. Here's terminal B. Here's terminal C. I'm going to connect these guys together. I'm just connecting them with wires because we aren't told of any transmission line impedance to worry about. And then my second load, I might put down here. where this guy is drawing 30 kVA at a power factor of 0.75 lagging. And there's the A connection. Here's the B connection. And here is the C connection, like so. We are told that the line voltages at the loads, which is going to be the same thing as the line voltages at the source, since we aren't given any transmission line impedance, are 208 volts RMS at a frequency of 60 hertz. So essentially, I have 208 volts RMS between the A and B terminals here, and that would be the same thing as 208 volts RMS between the transmission line terminals of this second load, because they are connected essentially in parallel. Okay. We are asked to determine the magnitude of the line currents. So we want to know what IL is, and we want to know the power factor at which the voltage source is supplying power. So we're just trying to find IL and power factor. So we are going to do this pretty similarly to how we approached problems where we only were given load characteristics when we were dealing with a single phase system. So what did we do then? We calculated the complex powers and then use that to do essentially everything else, right? So what is the complex power absorbed by load number one going to be? And if you need to go back into your notes from when we were dealing with single phase systems to remember how to do this, go nuts. I'm like 97% sure I asked you guys to do calculations like this in homework set number one, problems, I think 2 and 3. So something over power factor on occasion, and then an angle of the inverse cosine of the power factor, right? So that something over power factor is average power, okay? So let me ask you a different question. Did I provide you with average power? No. What did I provide you with? So if it's not average power, it's either apparent power or reactive power, right? So which one? Apparent power, because the units are in kilovolt amperes. So complex power is apparent power angle, power factor angle. So this should just be S1 three-phase with an angle of the inverse cosine of power factor 1, okay? Which we were given our apparent power of 60 kVA. So that's going to look like 60 with an angle of, I think it's going to be 36.87. Yeah. So 36.870 degrees kilovolt ampere. And for what it's worth, I'm going to store this in my calculator as X. And I want you guys to tell me what the complex power absorbed by load 2 is going to be. I gave you essentially the same pieces of information, so you guys should be able to throw this in your calculator and figure it out pretty easy.
Would be 30, 41, 40.
Yep, 100% correct. 30 angle 41.4096, so 410 degrees kilovolt ampere, and I'm going to store this as Y. So let me ask you a slightly different question then. What's the total complex power supplied by our voltage source? Exactly right. Yeah, 100%. That's why I stored it in my calculator, so I could literally just do that. And so I got, sorry, 89.937 and some change with an angle of 38.383 degrees kilovolt amperes. And I'm storing that as Z. So before we move on from here, I want to make sure that you all got the same result. Okay. Disastrous. Okay. So 89.937 angle 38.383 is what I got stored and stuff in my calculator. So I feel pretty strongly that I'm correct there. So how are we going to solve for the line currents in our system or the power factor at which our voltage source operates? I feel like we can do the power factor pretty easily because that is just identical to what we've done before. So having this information, how would we calculate the power factor of our voltage source? Cosine of that 38.383 degrees angle. Yep, 100%. So the power factor at which our voltage source operates is going to be the cosine of 38.383 degrees. So cosine of what I have stored in my the polar angle of what I have stored in my calculator as Z, and I get 78.388, or actually, let me do it like this. 0.784. Is this going to be leading or lagging? Why is it lagging? Because it's positive. There we go. Okay. So we've got our first quantity related to our three-phase power analysis. Now we need to figure out how the hell we're going to get IL. Okay. So let's go back to these relationships here. Okay. So the easiest one to solve for what IL is going to be is actually going to be using our apparent power relationship. Okay. So we have the expression over here. Let me just underline it for you guys. Root 3 times the magnitude of our line voltages times the magnitude of our line currents is equal to our apparent power. So if I come back over here and I rewrite that equation, I have the magnitude of SVS three-phase is going to be equal to √3 VL IL. So I could rearrange this and say that IL, the quantity that I'm looking for, just the magnitude of my line currents, is going to be my apparent power divided by √3 times my line voltage. Well, I'm told up here, the line voltage is 208 volts RMS. So what is my apparent power in this system? So 89.937 kilovolt amperes divided by √3 times 208 volts RMS. So with the units I have right here, this is going to give me a current that's measured in kiloamps RMS because I'm dividing kilovolt amperes by volts RMS. So let's see. The magnitude of Z divided by the square root of 3 multiplied by 208 gives me a current of 0.24964 kiloamps RMS, or 249.641 amps RMS. Let me just scroll up here. There we go. So our our power factor calculation, again, that is pretty much exactly what we did when we had single phase systems, right? So that should have been fairly familiar. In order for me to calculate this current that we were looking for, all I was doing when deciding which of those multitude of equations that I wound up giving you was which is the easiest one to use based on the pieces of information that I either was given or had already calculated, right? So I knew that when we calculated our total complex power, we had access to our apparent power, which is just a very simple equation. And we were also given what our line voltage was. So that's why I chose to use this equation right here, because there's only one thing I don't know if I use that guy. Realistically, I could have also used this one, but that's just introducing a phase angle that I have to deal with that isn't remotely necessary if I'm just trying to find the magnitude of the line currents. If I was trying to find the real value of the line currents, so like it as a phasor, I probably would have just used that complex power relationship up there and rearranged it. Okay. So let's look at the second problem here, unless anybody has any questions about this one. So for this guy, we have a balanced three-phase source that is powering 4 different loads. So drawing this would be a little bit of a pain in the ass, but essentially I could do it like this, except that I would expand it out and then just put more loads connected to each other, but they're all going to be connected in parallel. I'm given all of these pieces of information about the loads. I'm told that the line voltages at the loads is 600 volts RMS, and there is a line impedance of 0.02 plus J 0.04 ohms. and I'm asked to calculate the magnitude of the line voltage at the source. Actually, I might need to draw this out just so that we can really picture what's going on. And then I want us to calculate the power factor at which our source is supplying power. So let me attempt to draw this god-awful thing. So here is our balanced three-phase source, yet again. Terminals A, B, and C. Here's my transmission line impedance, ZW. And now I've got 4 loads connected in parallel. So I'm just going to draw myself a long stretch of wire here. Let's put load 1 over here, just for the hell of it. So it's absorbing 20 kVA at a power factor of 0.80 lagging. And then I'm going to try to put 3 boxes down here representing the other loads. Here's my A phase, B phase, C phase, let's see, this will be load 2. So that's 10 kVA at a power factor of 0.7 leading. Here's load number 3, which is drawing 10 kilowatts at a power factor of 1. And goodness, here's load 4. That's drawing 10 kilowatts at a power factor of 0.6 lagging. Our ultimate goal is to figure out what our line voltages at the source are. So I'm just going to put that here. We're just looking for the magnitude of this voltage, lowercase ab. And we're also trying to find the power factor at which our source is supplying power. So the magnitude of VAB is equal to something, and the power factor of our voltage source is also something that we're looking for. Okay. So we're going to approach this guy pretty darn similarly to what we did earlier. Okay. Another thing that we know for what it's worth is that this voltage right here, the line voltage is at the load is 600 volts RMS. Okay. All right, so how do I calculate the complex power absorbed by load 1? Yeah, so it'll be 20 kVA cosine 0.8. Excuse me, inverse cosine of 0.8. So that'll be 20 angle 36.870 degrees kilovolt amperes, and I'm going to store that as X. Somebody else tell me how to calculate the complex power absorbed by load number 2. So the negative should go out in front. But you're right. So anytime we have a leading power factor, we should get a negative angle. So that's why that negative value is out in front of the inverse cosine operation. So just throwing that into my calculator real quick. I get 10 angle negative 45.573 degrees kVA, and I'm storing this as Y. What about load 3? Anybody else? 100%, because it's operating at a unity power factor. Absolutely right. So 10 kVA angle inverse cosine of 1 is just 10 angle 0 degrees kVA. So I'm going to store that as Z. Yes.
Oh, what is raising kilowatt?
Right, but the kilowatts divided by our power factor of 1 is going to give us that in kilovolt amperes. So essentially, because our load is purely real, it's absorbing both 10 kilowatts and 10 kVA with an angle of 0. So Ricky, how about you tell me what's going on with load number 4 if you can? Right. So how do I get the apparent power from that? So whenever I'm given average power, that's the case where I have to divide by the power factor in order to convert it into apparent power, right? So 10 kilowatts divided by my power factor of 0.6. And then my angle is going to be the inverse cosine of 0.6. And so I got 16.667 with an angle of, oh, that's not right. I didn't do inverse cosine. There we go. 16.667 with an angle of 53.130 degrees kilovolt amperes, which I am storing in my calculator as T. So what is the total complex power absorbed by my composite 4 loads going to be? Just add all those together. Yep. So X plus Y plus Z plus T which I got to be 46.690 with an angle of 22.931, actually 932 degrees. kVA, and I'm going to store this in my calculator as lowercase a. Glad my calculator has 8 things to store to. Okay, so we've done a whole hell of a lot of work here in order to figure out what's going on with our composite load. Okay, so let's think about things really quickly. Our ultimate goal is to figure out what's going on with the voltage drop across the terminals of our source, as well as the power factor at which our source is supplying power, okay? So I would argue that in order to figure out either of those things, we're going to need to know essentially the complex power supplied by our source. And looking at this system, I hope you guys can agree that the complex power that is supplied by our source is the same thing as the complex powers absorbed by our loads, but also the complex power absorbed by our transmission line network. Because since that's not an impedance of 0, it's going to be absorbing some power as well. So how are we going to sort out the complex power absorbed by our transmission line network? So to some extent, yes. So if we could figure out the complex power absorbed by one of those ZWs, and we multiply that by 3, that'll be the complex power absorbed by all of them, because they're all going to absorb the exact same amount of power in a balanced system. So we need to figure out whether or not it's going to be easiest to determine the voltage drop across that impedance ZW or the current flowing through that impedance ZW. The current, exactly right, because the current flowing through that impedance ZW is the same current that's flowing through our composite load, okay? Now, I hope you guys remember from homework set number 1, problem 1, as well as some of the example problems that we worked in class, that we could find the complex power absorbed by an impedance using in a single phase system. So we had the following relationships, right? We had V times I conjugate, or we had the magnitude of the voltage squared divided by the conjugate of the impedance, or we had the magnitude of the current squared times the impedance. I'm going to try to use this guy right here. So if I can just find the magnitude of the current, that's the only piece of information that I'm missing in order to calculate the complex power absorbed by those transmission line impedances. So how do you think I'm going to find the magnitude of my current? It's exactly what we did in problem 1 when we found our line current, because that's literally what we're looking for, right? So we have the magnitude of our line current is going to be the apparent power absorbed by our composite load divided by √3 times the voltage drop across our load. I'm using that double L subscript, so that's the line voltage of the load. So that's going to look like 46.690 kilovolt amperes divided by √3 times 600 volts RMS. So let me throw that in my calculator real quick. So the magnitude of what I have stored in my calculator as A divided by √3 times, and I believe it's 600. Let me just double check that. Yep, 600 volts RMS is the line voltage at the loads. And I wind up getting a current of 44.927 and some change amps RMS. And from here, the complex power absorbed by our transmission lines is going to be 3 times IL. Actually, I don't even need to put magnitude absolute values there because we're already dealing with a magnitude. 3 IL squared times ZW, where the 3 comes from the fact that we are dealing with a 3-phase system, right? So each of those individual transmission line impedances are going to absorb IL squared times ZW, and because I have 3 of them, I'm just going to add all 3 of those together. So that's 3 times my answer squared times my impedance up here, which was 0.02 plus 0.04 I. So that's, let me write this out. 3 times 44.927 amps RMS squared, 0.02 plus J 0.04 ohms gives me 270 angle 80 point, goodness gracious, I'm losing my damn mind. 270.806 with an angle of 63.435 degrees. Volt amperes. So this one is not in kilovolt amperes. I'm going to store this in my calculator as B. And so the complex power supplied by my voltage source is just what I have stored in my calculator is A, that was all the loads added together, plus what I have stored in my calculator is B. And I need to make sure that I use the units of kilovolt amperes for A and just regular volt amperes for B. I wound up getting 43,760.546 and some change, angle 24.564 degrees. Volt amperes is the complex power supplied by my source. So before we use this, we've done a whole hell of a lot of preparatory work to finally answer the questions that we were asked. But before we do that, does anybody have any questions, comments, or concerns about how we got here? Yes, let's start with you first, and then I'll get to you.
Why do we find IL right there if it's given to this question?
Where was it given to us?
Oh,
All right.
I was gonna add the ELL, I didn't know the 600 volt minus.
Yeah, so 600 volts RMS is the line voltage at the load. So I'm using that double L subscript for, so V is voltage, L is for line, and the second L is for loads. To differentiate from this VLS, which is the line voltage at the source that we're looking for.
I just wanted to make sure I understood.
Yep. Oh, yeah, sure. Yeah, so it was given in the problem statement. Any other question about this process or anything? Brandon, I think you were about to raise your hand, maybe? So just to be clear, did you get this 46,000 thing right here? Or 46.690 kVA? You got that. So notice that that units here are in kilovolt amperes. So I would take this guy, multiply it by a factor of 1,000, and then add that guy together because the units of kilovolt amperes is 1,000 times larger than a volt ampere. The only thing I can think of is that it was a unit problem, unless I typed something in wrong, which is always possible. So if somebody else got something different than me, please let me know. Oh, goodness. So I did not store that thing in my calculator as B, so that's part of the issue. Okay, so my thing is definitely an error. Let me try doing A plus B again real quickly. So I got 46. Let me fix this. Yep. Yeah, so 46,896.128. And then the angle is 23.147. So I'm glad you said something so I would look into it. I just assumed I was right because I assumed I'd remembered to store that number in my calculator as B. I just said I was going to do it and didn't actually do it. Yeah. Oh, goodness. No. All right. So I think we're okay with how we got to here. So how can we use this result of the complex power supplied by our source to calculate either the power factor at which our voltage source is operating or the line voltages at our source? Exactly right. So power factor of our voltage source is just going to be the cosine of 23.147 degrees. So what I just stored in my calculator is C. So let's see. The cosine of the polar angle of C, I get 0.9195. So let's call that 920. And is that leading or lagging? Lagging. All right, so how am I going to find the voltage drop? VLS. So let's look back at this relationship right here, right? So we just calculated a moment ago total complex power supplied by our voltage source, and we're trying to find the line voltage at our source, right? So we have apparent power. We have our line current because the current that's flowing through the transmission line is also the current that's leaving our voltage source. So those are the same quantities. So I think we can just rearrange that apparent power relationship again. So we could say that VL is just going to be our apparent power divided by √3 times IL. So that's going to look like 46,896.128 divided by √3 times 44.927 amps. Sorry, this guy up here should be in volt amperes. So let's see. the magnitude of what I have stored in my calculator as C divided by √3 times that 44.927 and change. I got 602.650 volts RMS. So that one was a bit of a long one, but it was only long because I gave you 4 loads to deal with. That problem did actually involve having to deal with having some transmission line impedance, so we had to go through and solve for a couple of extra things. But overall, the process that we had there was fairly similar to what we saw in the first problem. So before we move on to problem number 3, does anybody have any further questions about this guy? All right. So, in this one, we're going to have to work backwards a little bit, okay? So we have a balanced 3-phase source that is powering 3 loads, 2 of which we have information about, and 1 of which we don't. That being said, we are told that the total apparent power absorbed by the composite load is 35.52 kVA, and the power factor at which our source is supplying power is 0.88 lagging. We are asked to determine the average power specifically by load 3 and the power factor at which load 3 is absorbing power. So we're looking for just the information about load 3 ultimately, given that we know what load 1 is doing, what load 2 is doing, and what the composite load is doing. Okay. So, I guess I'll draw a little picture here just for the hell of it. So we've got our voltage source over here on the left. Unless I'm missing something, I didn't see any mention of any transmission line impedance that we needed to deal with. So I'm going to treat ZW as if it were a short circuit. So over here will be load 1, and then down here will be loads 2 and 3. So load number 1, we have 24 kVA, power factor of 0.6 lagging. Number 2, we have 10 kilowatts at a power factor of 0.75 lagging. Number 3, we have P3 is equal to question mark and PF3 is equal to question mark because that's what we're ultimately trying to find. We are told that the line voltage at our loads is 208 volts RMS. We're told that the apparent power absorbed by our composite load, so S composite 3-phase absolute value is 35.52 kilovolt ampere, and we are told that the power factor at which our voltage source is supplying power is 0.88 lagging. All right, so what's the total complex power absorbed by load one? Somebody who hasn't answered any questions, maybe help me out with that. This is the third or fourth time we've done this calculation, so hopefully it's old hat by now. Exactly right. Thank you. So 24 angle inverse cosine of 0.6. And I get 24 angle 53.130 degrees kilovolt ampere, and I'm storing that as X. Somebody else tell me what's going on with load two.
Kilowatt divided by 0.75.
Thank you. Goodness gracious, my penmanship is getting shitty, but thank you for that, Thomas. 100% right. So I wound up getting 13.333 with an angle of 41.4096. So let's call that 410 degrees kVA, and I'm going to store that as Y. All right, so we can't do anything for load three just yet. So what about our composite? So it gives us our apparent power. And then we are told about the power factor at which our source is supplying power. So because we don't have any transmission line impedances to deal with, the power factor at which our source is supplying power is going to be the same thing as the power factor at which our load is absorbing power, right? Or our total load is absorbing power. So we can use those two pieces of information, and we could say that we're going to have 35.52. I think that's kVA, yeah. At an angle of inverse cosine of 0.88. And I get that to be 35.52 with an angle of 28.358 degrees kilovolt amperes, and I'm storing that as Z. So using that information, how do we get the total complex power absorbed by load three?
Subtract the top or the total by the other two.
Exactly right. Yeah. So Z minus Y minus X, 100%. Oops. And I got 13.088 with an angle of -58.403 degrees kilovolt amperes, and I'm storing this as T for what it's worth. So my question to you all is, how do I get either the average power or the power factor at load 3 is operating at from this? So cosine of that angle is going to be our power factor, sure. So PF3 is just going to be the cosine of -58.403 degrees. So that would be the cosine of what I have stored, or excuse me, of the polar angle of what I have stored in my calculator as T. And so I got 0.5239, so 0.524. Is this leading or lagging? Leading because it's negative. All right. So how might I get my average power then? What did I do last time? I don't think I've calculated average power today. Put it in rectangular and then just take the real part of that. Absolutely right. Let's be as lazy as possible. Why the hell not? Great job. So if I take my result here, so S3 three-phase in rectangular. So let me just do what I have in my calculator as T, convert it to rectangular. So that looks like 6857.600 minus J 11,148.106 volt amperes, which means this part right here, the real part, is the average power. So P3 is 6857.6 watts, or 6.85, goodness gracious, 8 kilowatts. Ooh, great job.